So back to this problem that we were looking at, we are looking at two objects that both have mass, which most objects do, or all objects do, and they both have a net charge of 3 microcoulombs. That means just a bunch of electrons were taken away from each one of them. They're both positively charged. How do I know? Because there's no negative up here, so it must be positively charged. The electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. They're 50 centimeters apart, and we want to actually compare how strong the gravity force is between them as well as the electric force. And the idea is to show you how much stronger the electric force is going to be. So here we do the gravity force. We put G, which has got that constant G, mass of the first object, mass of the second, divided by R, squared the whole thing, and we got a force of 4.27 times 10 to the negative 13 newtons. However, as far as the charge is concerned, we put K in here, 9 times 10 to the 9 times 3 times 10 to the negative 6. Remember, 1 microcoulomb is 3 microcoulombs is saying 3 times 10 to the negative 6 coulombs. Every time you see this micro, you could just replace it with times 10 to the negative 6 and be done with the micro um, prefix, and everything would be in coulombs for you. You do need to keep it in coulombs if you want to calculate the force in newtons. So here's 3 microcoulombs, so they're both the same, and zero point 0.5 squared, so that's the distance between them, 0.5 meters. Again, the distance has to be in meters, and we see that it is 0.324 newtons. That's about 13 orders of magnitude, or rather 12 orders of magnitude, or 10 to the 12 times as large, um, and give you an idea of how much stronger the electric force is than the gravitational force. Of course, if both charges were negative, the force would be repulsive. If one was positive, one's negative, it's attractive. And so if one Q is positive and one Q is negative, you're going to get a negative answer. If both are positive, you'll get a positive answer. If both are negative, you get a positive answer. So positive is repulsion and negative is attraction. Okay? And last class, we were talking about the electric field, and that's basically how one object knows the other one is there. I mean, Earth creates a gravity field. If I suddenly teleported you somewhere a mile above the Earth pulls you, and how does it know you were there? I mean, you don't call the Earth and say, "Hey, bro, I'm here. Give me a call. Pull me down." It says, "No, it's just that you come into the field of the Earth." And so, same thing with electric charge has an electric field around it. And in a positive charge, the field lines always come out of the positive, go into the negative. So here's a problem. It's not showing up too well up here. I guess it's because of Schoology, but we have two electron and a proton. That should be a positive if it's a proton. Two charges, well, then they're both electrons, I guess. We're calling them P and E for some reason. Both negative 1.6 times 10 negative 19 coulombs. There's just one electron here and one electron here. And so we are going to find the force between two electrons that are 1 meter apart. So here you put it into our equation. The force is going to equal to K. Here's K. Here's Q1. There's Q2. And there's your R. You put it all in your calculator, and I hope you guys know how to use the E key on your calculator. It really used to save a lot of time. And so you come up with the answer of 2.3 times 10 to the negative 28 newtons, a really tiny force between two electrons that are 1 meter apart. Electrons, of course, are usually far closer than that. Two electrons 2 meters apart. What is the force between them, and what direction is it in? Now, you could go in and calculate the whole thing all over again by putting in 2 times 1.6 times 10 to the negative 19 coulombs for each one, and figuring it out that way. But yeah, I know that if I took two electrons um, and I put them 2 meters apart, that means I'm doubling the number of electrons. So if I double the number of electrons, I'm going to have 4 times the amount of the force because I doubled each electron, 2 here, 2 there. So the force just went up by a factor of 4. But then I take it 2 meters apart, so the force goes down by a factor of 4 because I doubled the distance. And so now the force would end up being the same. Okay, so I doubled the number of electrons, but I doubled the distance too, and that ended up compensating for each other. All right.